Welcome everyone to this session of our TIAS seminar. Today we are glad to receive our next speaker. This time our speaker is Professor Andrew Zammit-Mangion. He's an associate professor with the School of Mathematics and Applied Statistics at the University of Wollongong, Australia. He has expertise in the field of spatio-temporal statistics and its applications to the environmental sciences. He's recipient of the 2020 Abdel El-Shaarawy Early Investigators Award from the International Environmetric Society and the 2022 ENVR Early Investigation Award from the American Statistical Association section on statistics and the environment. We are so glad to have Andrew here, and the today's session is as follows. We have 40 to 45 minutes for presentation and approximately 15 minutes for questions. Without further ado, I leave the floor to Andrew. Andrew, you can start.
Yep. Thanks a lot, Ignacio. Thanks to the TIES team for inviting me. I'm very fond of TIES. I think it was 10 years ago when I attended a TIES meeting in Alaska and Anchorage. It was such a great meeting, and that's where I think I got the drive to work in environmental statistics, and I've never looked back since, really. So I'm from the University of Wollongong in Australia. Wollongong is a beautiful seaside city just south of Sydney, 80 kilometers south of Sydney. So if anybody is ever in Australia, down under, and wants to visit, we're very welcoming, and we're always happy to have a chat. So the talk title, Bayesian Inference on Carbon Dioxide Surface Fluxes Using Satellite Data, is self-explanatory, I think, but I'll talk a lot about the individual terms which appear in the title throughout the talk. This presentation was done in collaboration with Michael Bertolacci, who's a postdoc here at NIASRA, and also Noel Cressy. And there are many more members involved. I'll talk briefly about that later. All right, so the main topic of this talk is the wombat. Of course, we won't be talking about the animal, the wombat, but the acronym WOMBAT, which stands for Wollongong Methodology for Bayesian Assimilation of Trace-gases, is the main focus of this talk. So the wombat, the animal, is a very cute animal here in Australia, and I like to call it the teddy bear of the Southern Hemisphere, because they're just so cute, and that's what you have as a soft toy, not a teddy bear here. Right, so WO is for Wollongong, M is methodology, and BAT is for Bayesian Assimilation of Trace-gases. So I'll be talking about a Bayesian hierarchical framework. Assimilation, it's because I will be talking about the fusion of numerical model output, in this case a chemical transport model, the output from a chemical transport model with some observational data, in this case satellite data. And we are focused on trace gases. So a trace gas is any gas in the atmosphere apart from the big three. The big three are oxygen, nitrogen, and argon. Anything else, which is the last 0.1% of the atmosphere, is a trace gas, or is made up of trace gases. Now, we are mostly interested in that 0.1%. That's where you find carbon dioxide, methane, nitrous oxides, CFCs. So a lot of work goes to try and see what's happening to that 0.1% of our atmosphere. So many people are involved in this project, which I really started working on together with Noel Cressy about 6 years ago now. So it's myself in statistics, our postdoc Michael Bertolacci in statistics, and Noel Cressy in statistics. But we had lots of inputs from atmospheric chemists, including Jenny Fisher here at Wollongong, Matt Rigby at Bristol, and Stavert at CSIRO, which when we started the project, she was at Bristol as well. Yi Chao on the IT side. And we had lots of conversations with many other people from the satellite CO2 flux group. They gave us a lot of input, and also I list some names here also who we've had some very important discussions with. They're all atmospheric chemists over the years in order, and this all helped bring us to the stage where we are at today. So why is this framework important? So WOMBAT will soon be part of an international Model Intercomparison Project, which involves researchers from all around the world, including NASA and NOAA, and others from other science institutions and universities. So there are about 13 to 16 groups around the world who try to use satellite data to find carbon dioxide sinks and sources from the satellite data, okay? And we count ourselves as one of those groups at the moment. And also next year, WOMBAT will contribute to a report that will be submitted to the United Nations Global Stocktake. This meeting, which will happen in 2023, is really to see where countries are in tracking their carbon dioxide emissions, to see whether they are on track or not, things like that. Now, countries are self-accountable to report their emissions. So they estimate their emissions by, estimating the number of cars they have, how much wood they are burning, the power stations, what are they emitting, things like that. And that's what we call a bottom-up approach, trying to go to the basics and building up. And that can lead to significant uncertainties when aggregating, especially over large areas. What we're doing is the reverse. We call this a top-down approach, where we see what the satellite data is, what's carbon dioxide doing in the atmosphere, and then try to go backwards in time, essentially, and see where the carbon dioxide came from or where it went. And that's actually a much harder problem, mathematically at least, but it gives you a much more objective assessment of what the real state of the net carbon emissions is across the world. So why is carbon dioxide an important gas? So I think I'm preaching to the choir here, but every time I see this graph of the amount of carbon dioxide in the atmosphere, which we measure in units of parts per million. So you take 1 million molecules and you see how many of those are carbon dioxide, basically. It's just increase, and the increase is so dramatic over such a relatively short amount of time. It is worrying, even if we didn't know what this gas does in the atmosphere, which we do know. It would still be worrying, because this is a massive increase. Okay, it's like a 30-40% increase in 60 years. Now we know carbon dioxide is a greenhouse gas. It will cause, and it is causing, global warming, and the worrying thing is that even if we keep our net carbon emissions to be the same, this at the moment we'll still get an increase, right? So we actually need to get a net zero in order for this to remain constant, and then we need a net decrease in order for this to start going down. So it is a global problem, and one which is actually very difficult to solve. So why is this flux inversion problem, which is looking at data from satellites on carbon dioxide and trying to see, where it came from and what countries are doing, why is it such a difficult problem? And the reason is that once carbon dioxide is emitted, it mixes very quickly in the atmosphere. So you're going to emit it today, and in 15 days time. So what we've done here is we've switched on the US, and we've assumed the rest of the world is off, not emitting anything. And then we've seen the effect of the gas, like what does the gas do in the atmosphere? And okay, in the first day, there's not much. It's mostly in the United States, and then it starts swirling around. This is 15th January now. By the 1st of February, it's basically all across the Northern Hemisphere. And by the mid of February, it's the Northern Hemisphere is nearly constant. It's not, but it's nearly constant, the mole fraction there. So if I observe something today, I need to actually go backwards in time and see where it came from. And it's actually a very complicated problem. So I'm going to share my screen now and show you a video of what this looks like in practice. So this is exactly what I've talked about. We are switching on the US emissions for 1 month, and then we're switching them off. So the cumulative emissions will flatten in February. And then we see what the gas does. The gas doesn't just disappear, right? It's going to be swirling around in the atmosphere. Okay, so we've switched on the United States. It's emitting carbon dioxide. And in February, we're soon going to switch the United States off. as well. So now there are no emissions across the globe, but the gas is still there and it's still going around. So our satellites are retrieving carbon dioxide concentrations in the atmosphere, but we're in February now, and we've got about 1/4 of a ppm in the northern hemisphere. And it's not just the United States which is emitting the gas, all right? There's every country in the world is emitting carbon dioxide. And of course, there are natural sources and sinks as well. And not only in January, in February, in March, in April, and May. So what we get is this big confusion of contributions, let's put it that way, to when we observe how much parts per million there is at this point in space and this point in time. It's very hard to say exactly where this came from and when it came. So that is why this problem is often known as a nilpost problem. Okay? Mathematically, it's a nilpost problem. I'm going to go back to my previous slides. All right. So the efforts to reduce net carbon dioxide emissions must be global, and we need to know, where the emissions are, where the sinks are, and we know the strength of the emissions and the sinks. And you'd think that by now we really have a good understanding on, what regions are the biggest sinks of carbon dioxide, which are the sources. But actually, there's lots and lots of uncertainty still around, the extent to which oceans are sinks of carbon dioxide. What's happening in the extratropics. We have this big seasonal cycle, which we'll see a lot later in the talk. Exactly how much is the biosphere absorbing carbon dioxide. So the biosphere is, fortunately for us, a net sink, but we are emitting much more than what the biosphere is absorbing. All right, so let's start talking about the main model in WOMBAT. So we're going to have what we call a multivariate spatiotemporal process, because we have two spatiotemporal processes of interest here. The first one is what we are primarily interested in. Okay, this is called the flux field. So these are the sources and sinks of carbon dioxide, and those are measured in kilogram per meter squared per year. And what we've done here is simply taken a plausible flux field, and I'll say how we describe how we come up with a plausible field later, and just averaged it for a whole month. Okay, so and this is January, so you can see that, for example, the northern extratropics, all the trees have lost their leaves mostly, so they're not really absorbing carbon dioxide. There's not a lot of sun during the year, these months, sorry. So actually you have a net sink over here. In summer, this will become a net source, okay, this will become a net sink of carbon dioxide. But what we observe is not this, okay? What we observe is the carbon dioxide mole fraction in the atmosphere. So this is the emissions that have gone up in the atmosphere, they're swirling around. And this is an example of a mole fraction field, column averaged. Okay, so imagine I'm looking at it from space, and I'm just taking an average at every spatial location over 3 hours at midnight in January 2016, 1st of January 2016. Okay, and this will change every 20 minutes. We simulate at a 20-minute resolution. Actually, this field changes quite quickly. And again, so we want to go from this to this. But the problem is even more difficult than that, because we don't observe this. We can't observe the whole Earth at one point in time everywhere. It's just impossible, right? We've got satellites and ground stations, but what we observe is more something like this. Okay? So Z2 is the observations of what I call Y2, which is the mole fraction field. Okay, and the Y2 is actually a 3-dimensional space-time field. Okay, so space, height, that's a geopotential height. And T would be the time, UTC. But what we observe is actually this thing over here. Okay, so this is data from the OCO2 satellite, Orbiting Carbon Observatory-2 satellite. It's in a sun-synchronous orbit, which means that when it's going round, it's always roughly around midday local time, wherever it is. And it's got a 16-day repeat cycle, which means it's going around the Earth, and after 16 days, it will start overlapping its previous tracks. These are called tracks, okay? So it's, you can imagine it going around the Earth, and it's taking soundings, and what we get are mole fractions in parts per million, very close, sometimes directly under the satellite, sometimes slightly off, where we call that the glint mode, but those are details. And what we observe is something like this. Now, the satellite actually retrieves carbon dioxide in the vertical dimension as well, but those are very unreliable. So what we end up doing is using a column average, the pressure weighted average of the carbon dioxide in a vertical column as our data. Okay? And I'll talk more about that later. So the Bayesian hierarchical framework looks something like this. So we've got the satellite, this is a picture of the OCO2 satellite. It's giving us this data. Okay, it's a spatio-temporal data set, quite big, hundreds of thousands of data points for the study we consider. So Z2I, so each measurement would be a column average. This is a column averaging operator, AI, of the mole fraction field at some point in space, at some point in time. The height here is averaged over, that's why I've done a dot. We know that the retrievals from the satellite are biased. So we're going to add a bias term over here. And we also know that there's some random error, and we call that measurement error. Okay, so that epsilon I will just say it's normally distributed with some variance. I should say that this AI over here is itself an inversion algorithm. Okay, so the OCO2 satellite reads spectra. Okay, so it looks at the light spectra. The way it works is that gases like carbon dioxide have got very clear absorption signatures in spectral space. So you take a spectrum, and if you see some frequencies which are greatly attenuated, then that is related to how much carbon dioxide there is in the atmosphere just below the satellite. But going from spectral space to actual ppm, there's quite a long process. It's an inversion algorithm. It's also a Bayesian inversion algorithm. But we're going to take those, actually the maximum posteriori estimates from that Bayesian inversion algorithm as our data. All right, so that's the data model, what I call the data model. But Y2, which is the mole fraction field, now this is over the whole globe. We need a model for that, and that is actually the transported flux. So we've got this linear operator on the flux. We're using G because it's related to the Green's function of a PDE. But just think of this as having some flux here, which we're denoting as Y1. These are the sources and sinks. We're going to transport them through the atmosphere, and that is going to give us the mole fraction Y2. Of course, chemical transport models are not, they're not perfect. There are some errors, mostly due to grid-based approximations, but also due to not getting the physics exactly right. So we've also got this spatio-temporal error term here, which we call transport error. But of course, the long-term goal is to estimate Y1. We're not that interested in Y2, okay? It's really the fluxes. So how do we go about that? We need a model for Y1, okay? Now, the flux field, if we had to model it at the grid level, so let's say we didn't care about computations and we just went for the finest resolution possible, okay, which is that of the chemical transport model. We are constrained by that. So the finest resolution we can go to realistically is about 2 degrees by 2.5 degrees. And that is about, and let's say we want a daily resolution, that's about 314,000 flux grid cells per day that we would need to make inference on. We actually want to make inference on 2 years of data, 2 years of fluxes actually. So if we multiplied this by 365 by 2, we get roughly 220 million unknowns, and that is of course way too much. Nowadays you probably can fit spatial stats models to that of that dimension if you used various approximations, but really within this hierarchical model, it would be impossible to make inference at that resolution, nearly impossible. All right, so what we opted for is to instead assume low dimensional representation of the flux field. So what we're going to say is that Y1, which is the flux, is some best estimate of the flux before we do the inversion, and we get that best estimate from databases like what the biosphere is doing, what were the fires, the forest fires, and all that stuff. But I'll mention those briefly later to come up with a good initial estimate of Y1 naught. And then we're going to use basis functions, and those basis functions are also physically motivated. They're not just sometimes we do splines, or they're based on splines or bi-squares or Wendland basis functions. No, they are actually physically motivated basis functions, which I'll talk about later. And then we're going to weight those basis functions by alpha ij. So what is I and j here? I denotes a spatial scope of the basis function, and j denotes a time point. So in fact, what we're going to do is divide the world into various spatial regions, and consider a monthly resolution. So we'll only be updating these basis functions. Will have a monthly scope, and then we're going to update the alpha j's. And you can think of these alpha j's as adjustments as causing an adjustment to our initial best guess of the flux Y1 naught. Now, these alpha ij's are themselves random. Okay, we're going to model them using simple autoregressive 1 processes. And the reason for that is because if our best guess, let's say, is wrong, let's say it's too low in January, it's probably going to be wrong as well by a similar amount in February. So that is the intuition as to why having these scalings correlated in time. That's why we do that. Okay, so we have a sigma squared I here, which is also unknown, and also a rho I here, which is also unknown, and then we would put priors on those. All right, so these are the spatial regions which I was talking about. Again, this comes from the atmospheric chemistry literature, why it is reasonable to split up the world into these regions when it comes to carbon dioxide. They're called transcom regions, and there are 22 of them. Now, this figure might give you the impression that we are considering basis functions that are constant within each region, but that's not the case. So every basis function will be spatiotemporally varying within each region. Okay? And the pattern, let's put it that way, of the spatiotemporal variation comes from inventories and databases. All right, so this gives us actually the full hierarchical model, excluding the hyperpriors. So I'm not talking about the hyperpriors, like a beta prior on the autoregressive parameter, but this is the main hierarchical model in WOMBAT. So we've got, just to recap, we've got data taking a column average of the mole fraction field, with bias terms and some random measurement component. The mole fraction field is a transported flux plus some transport error. The flux has some flux prior mean. This will be the mean because we'll take the expectation of the alphas to be 0. And then we're going to have this will cause the flux adjustment. Okay, so inference on the alpha is really our main target here, because that is what will give us inferences on the Y1, which is the flux. And then we've got the alpha ij's are following autoregressive 1 processes. We have one for every spatiotemporal region, and then we've got these residuals from the AR1 are modeled as 0 with variance sigma squared I, which we assume so the sigma squared I is per spatial region. Okay, it does not change in time. The importance of using basis functions is that we initially had 220 million unknowns, but if we use 22 transcoms on the 1 monthly resolution, then over 2 years you get 692 unknowns. Okay, so we've reduced the dimensionality of our problem dramatically. Okay, of course there's no free lunch. There are drawbacks to doing this, which we can discuss later. But this is essentially how we go around tackling our problem of dimensionality. Now, recall that the mole fraction field Y2 is given by this equation over here. If we do a mental substitution of Y1 here, which is this quantity over here, and substitute it into this equation over here, and we interchange the integration and summation, we get this model for Y2. Y2 naught would simply be the transported best guess flux, okay, of our prior expectation, essentially, and that will give us Y2 naught, which we can think of as our best guess mode fraction field. And now we're going to have the integration of G with the basis functions phi. And that's going to give us a new basis function. It's called as psi. But now psi is in the mole fraction space. Okay, so there's space, height, and time. I'll talk more about psi later. The interesting to note is that we've got our alphas, they propagate through, okay, they jump out of the integration. So although now this model is in mole fraction space, when we make inference on the alphas, we would implicitly be making inference on the flux field as well, okay, because Y1 is determined by alpha. Now this is just a big vector-vector product, actually, so we can write this equation more succinctly as follows, and we need to make inference on this alpha. So these psi ij's, if you recall when we did that mental substitution, essentially they're the transported flux basis functions. That's what they turn out to be. These are sometimes referred to as response functions in the literature. And well, how do we come up with these response functions? Well, we can't analytically do this. The chemical transport is really complicated. It's determined by meteorological fields, which are changing all the time. So how do we determine these basis functions? Well, we actually evaluate them at any point in space and time that we want using a chemical transport model. And how we do that? Well, we take our basis function, like what I showed you earlier in the video, which would have some local spatial scope and some local temporal scope, and literally pass those through a transport model. And that will give us what we call the response function, which is the basis function in mole fraction space. And this is where we start now hitting some computational issues, because running a chemical transport model is not simple in itself. I mean, first of all, we use GEOS-Chem. It's written in Fortran. It's its own beast of a software in order to get working. You need to get inventories, databases, all with different formats. But also it takes a long time. So if we want to take one basis function and simulate it forward for 2 years, we simulate at a 20-minute resolution, and you cannot really go much below that, and also at a grid cell level. So it will take many hours, even maybe a couple of days to simulate one basis function forward. And we need to do that for every basis function. Okay, so we will have 693 runs that we need to do. In a later version of WOMBAT, which we're working on at the moment, we've got an order of magnitude more basis functions. It's nothing you can't do on a supercomputer, okay, but this is what makes development slow sometimes. If there's a mistake or you realize something's wrong, I mean, you need to go back to the drawing board, rerun all those things. So development can be a bit slow in this area. So this is what, similar to the video I showed you before, you have the flux basis function, you transport it using GEOS-Chem forward in time, and this is what a spatiotemporal response function would look like, okay? So let's say we're considering a basis function. This would be our flux basis function, by the way, in January 2016. So the response function will have a bit of carbon dioxide here, concentrated over the whole North America, and by the middle of January, and then it's really spread across the northern hemisphere by mid-Feb, March. It takes a couple of years for this mole fraction to cover the whole globe. Okay? The interhemispheric mixing tends to be quite slow. Right, and those are our response functions, and we've got 700 of them, and they are three-dimensional space-time. Okay, so there's space, height, and time. So now we can substitute our model for Y2 in our data model, and actually we get a data model which is, I mean, at the end of the day, this is linear Gaussian, really, standard stuff. But I hope you appreciate the complexity in getting this basic linear Gaussian model. So we've got an averaging of the mode fraction field, which is of our best guess, plus the response functions multiplied by the weights. And remember that the weights are our target, our inferential target. We've got the transport model error here, which ultimately what we're going to do is simply model as a spatiotemporal field, okay, using approximations in the likelihood. I'll talk a bit about that later. And then we've got some biases, and then we've got some random errors. Okay. So what do we need to make inference on? Of course, the alphas, those give us the fluxes, the betas, those are the bias correction coefficients. mu2 here, the transport model, we're going to make inference on like spatial length scales and temporal length scales coming from the transport model. And epsilon would be the variance of our measurement error. Now, the retrieval, the OCO2 retrieval actually gives us measurement errors, but we don't really trust them. So what we do is we introduce an inflation factor for those variances, and we estimate those inflation factors as well. Okay, so we're going to use a Markov chain Monte Carlo. I'm not going to talk about the details. We have a paper in GMD which talks about all of this now. But essentially, there's a Gibbs sampling based framework. There's some slice sampling in there, some metropolis hasting, but nothing, nothing particularly extraordinary from an MCMC point of view. But the bigger challenge is, of course, is showing that you've got good mixing, that you've converged to the correct distribution. So Michael had produced these plots with hundreds of trace plots, and we looked at all of them actually to really ensure that all our parameters in our model are mixing well. The spatiotemporal correlation component, which is this nu2 over here, that's ultimately we have hundreds of thousands of data points. We do use Vecchi approximations. Essentially what these are is you break down a joint distribution into a product of conditionals, and then when the set of conditionals becomes really large, you start removing some of those things you are conditioning on. That gives you some sparse matrices, and things become a bit easier to work with. We had to use GPUs simply because there are lots of matrix calculations, and GPUs really helped us in getting some of those true. And then you just get posterior distributions on all your unknowns. So that's it basically. All right, so I'm going to show you quickly in the last 10 minutes some results that we got. So what we tried to do with WOMBAT is replicate the Model Intercomparison Project V7, which was published in 2019. So we were working on WOMBAT, but it wasn't really ready by the time they were doing the MIP, so we didn't take part. But what we did is still try to take part after the fact, let's put it that way. So we used their protocol, using data from September 2014 to March 2017, averaged the satellite data to 10 seconds. That was their choice. We're still not sure whether this is really a necessary step. We use GEOS-Chem, we use the GEOS-FP meteorology. You can use different meteorology. That will probably give you different results. This is one of the problems with flux inversion. There are many moving parts. Then you need to have these databases. I think I mentioned these earlier, to construct your basis functions, but also to construct your best guess flux to start off with. So this is, of course, a lot of work in itself, finding these databases. So we use fossil fuel databases, ocean fluxes databases, biosphere fluxes. So what is the biosphere doing? This is probably one of the most important. So what are the trees doing? Absorbing carbon dioxide, for example, animals, everything. Okay, there are models for that. So these biosphere fluxes. Biofuel fluxes, these would be things like wood fuel. So there are databases for that, and also biomass burning, for example, of this QFED, it's the fire emissions database. These track forest fires, which emit carbon monoxide, which eventually becomes carbon dioxide. So all of these have to be included in order for this framework to work. So why is WOMBAT different? I didn't really talk about that. So of course, there are lots of flux inversion systems around the world, and they all kind of work. But what they don't do is, for example, incorporate the bias terms in the model. They don't consider spatiotemporally correlated error terms. They don't consider uncertainty on the priors parameters, things like that. Basically, everything is done so that the system remains Gaussian, and at a relatively tractable dimensionality. And that comes with a lot of compromises. And what we've tried to do is develop a framework which can, not force us to make those compromises to just have a Gaussian model marginally. Of course, conditionally, it's still Gaussian, but there are lots of other moving parts in the model. So what we did was an OSSI. These are called an observation system simulation experiment. And what you do here is you simulate pseudo data, so OCO2 data, using a working model. And this working model is going to include biases and spatiotemporal correlations in our case. And then we're going to see what happens when we remove those biases in our model, and we remove those correlated errors in our model. Okay. So this is the model that we're going to generate data from. It's exactly what I showed you before. There's some spatiotemporal error term here. There's also some biases. These biases are again physically motivated. We know that the OCO2 data is biased when the retrieved surface pressure is lower or higher. The bias is a function of the retrieved surface pressure, the carbon dioxide at the surface, the pressure, the air pressure, the aerosol optical depth, all these things. There are others, but these are the main ones. So we actually generated synthetic data and incorporated these biases in. We also used some spatiotemporal correlation, and then we played a game where we either left them out in our model or put them in. And this is quite a difficult plot to interpret in the short amount of time we have. These are called diver down plots. This is I think it's because it's like following the trajectory of a diver who is diving. But diver down plots are used quite a lot in the space because there usually is a reasonable understanding of what total flux is. So for example, here we're comparing flux in the southern tropics to flux in the northern tropics, and and all inferences would generally follow this line because the total is easy to constrain. It's partitioning that total up into different components, which is very difficult. And what we show here is what happens when we, for example, remove correlation or remove biases in our models. And to cut a long story short, if you focus on this green one here, this is when we have no bias correction and no correlated errors assumed in our model, when the truth is in fact biased and has correlated errors. And the truth here, the true flux, is given by the triangle, okay? And you can see that this is way off when you assume there's no correlation or biases. The red is when you do assume correlation and biases, and you can see that, for 2015 and 2016, the red, the true value sits very nicely in the red ellipse, and that is the ellipse is given by 95% credible intervals. You can see that it sits quite nicely in there. That's to be expected because it would be the true model at that point. What is quite interesting is the purple one. This is when you have no bias correction in your model, but you have assumed that there are correlated errors. And you can see that it's off, but the credible intervals have widened up. So what that shows us is that if you are not if if you're not assuming any biases, the incorporation of spatiotemporal error term in your model can save you a bit. What has happened here is that probably it has attributed a very long length scale to the spatiotemporal error term that reduces the amount of effective information you have on the flux. That's why we get larger credible intervals, but actually, things look quite well. Maybe here and here they're missed, but at least in 2015, 2016 for the satellite mode, which is land glint, the true value is in the Alps. Anyway, we can play this game, and it was clear from our results that, of course, if the data is really biased and has correlated errors, then if you don't assume them in the model, you have problems. All right, so then we looked at the real data, of course. Again, lots of plots, which are hard to interpret in the short amount of time we have. But what we have here is that the light green are the results from the Model Intercomparison Project, which is the spread. Okay, so this is the minimum and maximum, and we have 2015, 2016. These lines are the prior expectations. We can ignore them for now. And the dark green then is our posterior distribution. So we're comparing apples with oranges a bit, because this is the spread of point estimates from 13 groups around the world, and this is our posterior distribution. And this is really just a sanity check to see that whether our framework is giving us reasonable inferences or not. It's hard to know just by looking at these plots, whether we're better or worse or whatever. But these plots really show us, and even here we've got zoned estimates, so northern extratropics, northern tropics. There are some you might call them issues, for example, here in the northern tropics, which actually have improved a lot in version 2. We have changed the model slightly, but that's a story for another time. Okay, we can estimate the bias coefficients online. This is a big strength of our approach. So what is usually done is people use what we call TCON data, which is total column carbon observing network data, for estimating the biases in the satellite data. So these are ground station data. They compare them to satellite data, and they come up with these bias coefficients. But what we can actually do is estimate them online while doing flux inversion, okay? And this is something relatively new. And what we can see, there are two modes of satellite data. So this is land glint data, this is land nadar data. Doesn't really matter. Our posterior distributions don't really capture what the group's estimate of the bias is perfectly, but you can see that we're in the vicinity of their estimate. It's quite remarkable that we can do this during a flux inversion process. Also, their estimate is only based on data at the TCON stations, while our estimate is based on the OCO2 data, which is everywhere in space and time, right? So their estimate is not necessarily as reliable as ours, or vice versa. We just don't know. But it's really reassuring to see that at least we are in the same ballpark. And finally, validation, and I'll conclude with this. Validation is very difficult in the flux inversion world, because we cannot get real, ground truth observations of the flux on the scales of things like countries. It's impossible. So what we do is we get those fluxes, and then we simulate forward using a transport model, and then compare them to ground station data, or in this case, TCON data, and see what the errors are, okay, the mean squared errors. So it's kind of a proxy way of validating your flux. And here we are comparing to the other groups. So land glint, which is the first inversion using land glint data, we actually got an RMSC of 1.19 at the, mean squared error, not root mean squared error, just mean squared error of 1.19. And that was better than actually every other group which did flux inversion. For the land nadar, we got 1.57. That is a bit higher, so I think we're about 4 out of 10 people to get using this metric, okay, of mean squared error at validation data location. So these data weren't used in the inversion. All right, so I'd like to conclude there. We are still working on WOMBAT. We're working on a WOMBAT V2 project, which models the climatology of the fluxes. That is our biggest change, but also splits the biosphere component into respiration and gross primary production. So it allows us to see which components are really contributing to the net biosphere exchange that we see. Okay, I'd like to conclude there. There are some references. Anybody who wants the slides, I'll be happy to share them. Thank
you. Thank you so much. Any questions? Any questions from the audience? You could write the questions in the chat, and we can ask to our speaker, or you could just unmute yourself and ask the questions. Okay, if there is no questions, let me start with one question, Andrew. Do you, based on this work, do you have any particular conclusion on some specific geographic area?
On the sources and sinks?
Yes, exactly.
We don't have any conclusion which is substantially different from, I'm trying to find the main thing here. We don't have any conclusions which are substantially different from what is already seen in the literature. So namely, the most notable thing is that this carbon cycle, okay, where you've got emissions, global net from the biosphere. By the way, these are emissions from the biosphere. So global net emissions in winter, big sinks in summer. And all we've done so far is given like another vote of what is happening, and that is going to be used in a model intercomparison project. Some things we do see which are very interesting, which I haven't talked about here, for example, the El Nino events, 2015, 2016. We see that in the fluxes, so you can see spikes like corresponding to those events very clearly, but that also has been published by the carbon community already. There's a paper in Science which talks about that, and we do see those effects as well. In WOMBAT V2, because we're modeling climatological effects, we're also looking at maybe changes in seasonality, things like that, but nothing is conclusive yet.
Oh, excellent. Any other question from the audience?
Thank you so much, Andrew, for such a great talk. I just wanted to ask you, can you give us a little bit more details about the transport term in your equation? I think it was your flux equation, the G function.
The G function.
I was just curious about it. Thank you.
No problem. So you can think of G as the impulse response function corresponding to a partial differential equation. We don't know, so the partial differential equations are implemented in GEOS-Chem. We don't know exactly what is going on. I mean, the GEOS-Chem is a project which has been going many, many years, and people constantly add things to it. We just wrote it down here mathematically because what is of import to us is that this is a linear operation. Effectively. So what does that mean? If we double carbon dioxide emissions today, then the effect of the response function, which is psi, will literally be double everywhere. Okay? There are some gases for which this is not the case. Okay, there are some gases which react in the atmosphere, and the more you emit, maybe the more they react. So those would actually have a nonlinear representation, and that would be problematic for us. So linearity is very important here because that means we can ultimately represent this as a matrix vector product, and the matrix is actually what we get out of GEOS-Chem. Okay, we literally simulate forward. You get a bunch of values, and you're going to arrange those in a huge matrix. Yeah, so does that answer your question, Dennis, a bit? Okay.
Okay. We have a question from Noel Chris. Nice talk, Andrew. You are showing the natural fluxes. How do you allow for anthropogenic emissions?
Yeah, so thanks, Noel. So we actually are, I didn't talk too much about this, but we are not modeling the anthropogenic emissions in this work. It's actually quite usual for anthropogenic emissions to be known because they're relatively well constrained. We need to know what is the net, the net flux in the countries, and so that would be the difference between the anthropogenic and everything else. The anthropogenic is really quite well constrained, so we assume those are known, and we only do the scaling factors on everything else. So, which would, in the case of this project, would be the sum of the ocean fluxes plus biosphere plus biofuel plus biomass burning, and that's how we construct our basis functions.
Thank you, Andrew. Any other question from the audience? Okay, we have a question from Josh Jacobson. Thanks for the talk, Andrew. Why is it important that we know where the fluxes are happening?
So thanks, Josh. This goes back to the main motivation. I think ultimately, we want every country to be responsible for its own, that it gets net zero flux. We only get net zero flux if we know what the biosphere is doing in that region, right? So that's why we need to know where, what is the net flux at that particular point in space and time. There are also other geophysical reasons. So for example, if the ocean is acting as a big sink, what are the implications of that? Okay, the carbon dioxide eventually sinks into the deep ocean, but there could be mixing, which then brings it back up to the top and can produce outgassing. So it can also change some more properties of the ocean. And so yeah, there are also the land ocean split is a big question actually, and lots of people are interested in seeing how much CO2 is actually going into the ocean.
Thank you. Any other question from the audience?
Question. Hello.
Yes, please.
This is Abdul El Shahawi is asking the question. It's interesting talk, and one of the issues that is quite interesting is the global transport model and showing the variation as things move in time and space. It's quite interesting. One of the things that really bothers me about this, that there is no experiment that show the pattern of the transport. When we are dealing with water, we can use traces to try to show the pattern we have. If we are talking about all these sources of CO2, then if you take, for example, the fires or whatever it is, and if there is a label, then you can try to follow the pattern that you can see, and you use this to calibrate the model and its flux rate, because it's you have quite a bit of difference between the different sources and how this is transported across continents and so on and so forth. And then what you have in Australia, you have lots of fires. And I just wonder if there could be some kind of an experiment to try to support the model.
So I know, thanks for the question, it's very good. So lots of discussion points actually. For local transport models, people use some trace gases like radon, which there isn't much of in the atmosphere, so they actually release it and see how it goes, and then they would have measurement locations and see whether their transport model is really capturing the evolution of the radon gas. For global transport models, honestly, I don't know what they do and how they calibrate them. The different inventory. So you were saying, for example, that there is more fires in Australia. So this is captured in the inventories that we use. And although, for example, we are using basis functions that are the sum of all these things, many people, and we're doing a bit of that in the next version, actually split those up. So you would have a basis function for biomass burning, a basis function for biofuel fluxes, so on and so forth. So if you have a basis function just on forest fires, then you could essentially find the scaling factor for the forest fire emissions. But of course, it gets even more complicated because every transport model can be run with different meteorology, which differ between themselves, and every transport model considers different physics as well. So even between themselves, there's GEOS-Chem. There's a nice paper in 2019 by Andrew Shu et al., which shows the differences in transport between GEOS-Chem and another transport model called TM5. And they differ a lot in, for example, the amount of vertical mixing in the atmosphere, even if they are driven by the same meteorology. And yes, we haven't considered the effect of transport, of having big discrepancies between transport models in this framework. We are at the moment actually conducting a separate study where we do inversions with more than one chemical transport model to try to get at least a bit of an idea how would the effect of the different transport on the inferred fluxes.
Well, I think one other issue that comes, we are talking about the fires in Australia or in Canada or whatever it is. But if you come in a country like Egypt and other places like this, I think the main source of CO2 that is coming in from Egypt, for example, is the cement industry. What you have a loading of CO2 to the atmosphere. And
Yes.
it would be quite interesting that this kind will lead to the result of trying to allocating.
Exactly. Yeah. That's true. So cement is included in the fossil fuels database of ODIAC. And we are fixing them. So we're assuming that what the countries and the companies in those countries report is accurate. But there are papers which show that there actually is a lot of uncertainty in these databases. So the current protocol is to fix these and not update them. But there seems to be a small drive that we should be updating these as well. Yep.
Thank you everyone for this discussion and questions. I invite everyone in the audience to unmute themselves and give Andrew a big applause for presenting the latest scientific contributions in their project WOMBAT. So please.
Thank you.
Thank you so much, Andrew. Thank you so much.
Okay, no worries.
Great
Thanks everybody for attending. Yeah.
Let me stop the recording.